we saw that it is possible to have model of the whole machine tool and predict what you could expect from the machining operations. This is great tool, but what you need is information about the machine tool, about its design, and this could be some limitations for this predictive digital twin. But sometimes you are user of the machine tool and you still need to clarify what is source of your errors. You need to check your process and be sure that your process was error-free. And here, digital twin, so-called post-processing digital twin, could be also really helpful. And therefore, I would like to welcome Mr. Albrecht Hänel. He is a researcher at Fraunhofer IWU, and he will present today Fraunhofer approach in this field of digital twins.
Okay. Thank you very much, Peter, and thank you very much for the invitation. And it's nice to have the presentation after Michael Sulitka, because I think we have the same vision about digital twins and the using of digital twins. And I will not say too much about the concept of digital twins, because I think that in this case or in this time, a lot of people are describe what it needs. When we are looking at the digital twin, we are focused on the manufacturing process. Maybe there are also other fields for focusing, but this is the focus of manufacturing. And there are a lot of main aspects for the creation. I think it is totally clear to have the data acquisition from NC, from PLC, from CAM or other information sources. Then I think that is one of the most important point is that you have an information model which will describe what are the relationships of this data you have to collect, and then to have the knowledge to enhance this digital twin, to get knowledge is to integrate relevant process and calculation models. And I think we see it already. We're also working on a software. Then you need a possibility to work with them. And when we take a look at the machining process, especially you have the side of planning data and you have the side of process data, and then you have to classify this data. And in our feeling, we see, okay, we have data about the workpiece, we have data about the process, we have technology data, machine data, and tool data, and everything we have to combine, we have to build up the information model. And this is just just named the shadow, because it's just data setting without knowledge, without information about. And then you have to integrate technological relevant models. So we already see path inaccuracies, tool engagement, cutting forces, surface quality. It's like a modular system, and then to bring it back, and then we have the shadow combined with knowledge or with models, and then we can call it twin. And when you take a look at the machining side, and we see, okay, we can equip a machine, maybe with an edge device or something else, to collect all the data. It is the left side. And this is all the high frequency data. So it means maybe 1 millisecond, 2 milliseconds, all we need, actual position, currents, and so on. There are some possibilities to collect all the data about some connections, maybe OPCOA, but it's for high frequency not so common, but also other connectivity systems. And then, and I think this is sometimes not so easy, is all the side next to the processes, CAM system, tool data management system, MES system, and this is static or low frequency data, heterogeneous data systems, and this is sometimes not so easy to handle. And then we have to bring it together in our unique standard for further processing, to describe all the properties and the relationships. And then our data enhancement will increase with all the models. And then we have the discussion about what is this data storage. And in our solution, we are working with the HDF5 format. This is a portable hierarchical data format, which is developed by the NASA. And there to have the possibility to store time rows and to store also meta information. And yeah, and then you have also other possibilities to store it, cloud systems according to Gaia X, something else. So in at least maybe one example, but there are a lot of more models. One example, I think an important model is a tool engagement. There we have to discretize the tool, what are the engagement situation, to have the local engagement, to get the angles, and maybe you can integrate some toolware calculation. It's depend a bit on your models you use. And after,
Sorry.
no problem. And after you will get a virtual workpiece based on the process data. So, and maybe a short view of our software, so you have the possibility to see what happened in the process with all process relevant data. All this virtual solution is based on process data. There is no NC interpreter or something else. It's just based on the process information. So maybe this is quite finished about our solution, our thinking about a digital twin, and I will bring or will say something how we use it, and we implement it in a company for a project partner, and there we equipped 2 machines with an edge devices. We connected it in our system, our computer system, and connected it to the Fraunhofer cloud, and all the time we collect the data according to our information model, and then we are sitting in our office and work what happened. And so it was possible, you see some chambers, some demonstrations to say, okay, what was the tool engagement along the tool part, what about the cutting forces, what happened there, so that you have a representation and of the discrete location, what happened on this process. And then you have the possibility to get a virtual component and to make some comparison to the actual geometry, and then you see, okay, what happened with your quality, what happened with your with your quality, or with your tool, something else. So, and now I have an example. I think it's a really impressive example, because it is, maybe Professor Ehrenfeld says in the morning something about it. Is a part in large structure component for the Athena telescope. It is the biggest ESA spacecraft project. The planned launch is 2034, and they plan with 2 billion euros. And the main part of this project is a mirror structure, and it is a machined, is an integral component with 4 meters diameter and with a height of 330 millimeters, and it is fully machined in one piece. And there we have integrated our solution, so it means we collected all the data, as you see, around 450, 440 gigabytes data with all the we collected all the time according to our model, and then it was possible to have the visualization of the complete process step with all necessary characteristics, and to see, okay, what happened, to see there are failures or nothing according to the material defect or the tool defect and so on. And it is a spacecraft component, and it is also important that you have a good documented process evaluation, and with our solution it is possible to have a process database quality control and process documentation. And so you have the possibility to see the tool paths, to make some investigation about what is the best milling strategy, to evaluate the process during the process, because this is an one-piece shot and everything must be clear. And yes, and with our solution we help to produce this part, and maybe 2034 we will see it in the space. So, and at least this is our Czech-German relationship or friendship, partnership. We built up a project together with TOS Warnsdorf, and there we also integrate our solution. And so we're building up our system together with the Technical University of Dresden and also with another company from Dresden, Cymate, so that we have also the possibility to store all the data and to bring it in our software to enhance the quality and to show what happened in the process. Yes, thank you very much, and hopefully everything is clear. When you have some question, please, after the presentation.
Thank you, Albrecht.